So let's work through an example of finding a tangent line or tangent plane and linear approximation. So we'll take the example where f is given by 2x squared plus y squared. So we've got this bowl shape right here. The graph is an elliptic paraboloid opening upwards. And we want to find the tangent plane and linear approximation above the point 1, 1. So since this is going to be on the graph, we're going to be looking for the plane that passes through 1, 1, 3, because that's the height at the location 1, 1. So here is 1, 1, and then up above it, let me see, so we've got a trace coming through one direction like that, and a trace coming through the other direction like that. And so directly up above there is this point right here. So this is the point 1, 1, 3. I guess maybe for clarity I should call the other one 1, 1, 0. So as a point in 3 space, it's 1, 1, 0. As a point in the domain of f, it's 1, 1, whatever. Okay, so let's see now. So I guess the first computation that I did, I didn't even write down, but I should have, and that was to find the height of the point above xy equal to 1, 1, and that's 3. Okay, so then what else are we going to need? We're going to need the partial derivative of f evaluated at various points. So first we'll just compute the partial derivative of f. And so d dx is going to give us 4x plus 0, and d dy is going to give us 2y. So the partial of f when we evaluate at 1, 1 is just going to give us 4, and the partial of y when we evaluate at 1, 1 is going to give us 2. So we can take this and put it together to get the tangent plane, which is going to be z minus z naught equal to x slope at x naught y naught times x minus x displacement plus y slope at x naught y naught times y displacement. And so for us, that's going to be z minus our height is 3, and then our x slope is 4, and we have x minus our x location of 1, and then we have the y slope of 2, and then y minus the y displacement of 1 also. And so that's our tangent plane, although typically people tidy it up a little bit, and so we would call this 4x plus 2y minus z is, and then collect all the constants to get 3. So there's our tangent plane. All right, now for our linear approximation to f, f is going to be approximately given by, and then we look at its value at this point, and then we add in all that stuff that we use for the tangent plane. So this business right here. And so in our case, we get that f is going to be approximately given by 4x plus 2y minus 3 near the point 1, 1. And so it might be worth pointing out that the tangent plane has normal vectors. So how do you find the normal vector? You do the old cross product. So the normal is going to be u cross v, which we can compute as, so let's see, so u is going to be 1, 0, and then our x derivative at a, b, and then v is going to be 0, 1, and then our y derivative at a, b. This is I, j, k. And so we work that cross product, and we get minus fx a b I hat and minus fy a b j hat plus k. So for our fixed point a, b, f of a, b, so if I make the third coordinate equal to f of a, b, then that ensures that I'm on the graph. Then the plane n dotted with p naught p equals 0 has the form, so let's see, so we've got n dotted p naught p, so our n was minus fx a b minus fy a b 1, and we're dotting this against x minus a, y minus b, z minus f of ab, and that's supposed to equal 0. So if we work out the dot product there, then we have, let's see, so multiplying together the first coordinates, we have the x derivative at this point times x minus a, and then from the second coordinates we have the y, negative the y derivative times y minus b, and then from the third coordinates we have z minus f of ab, and then we add all these up, and these are still equal to 0 as was on the other side. And now notice that if I take each of these guys and add them over to the other side, then we end up with the formula that we had before. So it checks out both ways.